Hi everyone, welcome back. In today's class, we'll continue the chapter electric charges and fields, and this is lecture number 5. Friends, in the last class we discussed electric flux. Now moving forward, we'll apply electric flux and we'll state Gauss law, and then we are going to talk about the applications of Gauss law, right? So let's start. First of all, what Gauss law is all about. Let's suppose that we have got certain charges over here, certain point charges like Q1, Q2, Q3, Q4, something like this. And we are drawing an imaginary surface containing these charges. This is an imaginary surface. So please note that we have said that this is an imaginary surface. The job of this imaginary the role of this imaginary surface is to contain the charges, right? To enclose the charges. So this is an imaginary surface. And also let's suppose that we have got some more charges which are outside of this surface. Let's say Q5, Q6, something like this. So Gauss law says that if you are going to actually draw an enclosed surface like this, so the net flux linked with this closed surface will be actually equal to the enclosed charge upon epsilon naught. This small statement is Gauss law. And we know that if we want to find out the net flux, we can also rewrite it as the surface integral of E dot ds, and further this thing can be written as enclosed charge upon epsilon naught. Now what do we mean by enclosed charge? In this case, enclosed charge will be actually Q1 minus Q2 minus Q3 and plus Q4. That means we will simply add all the charges along with their signs. This is going to be enclosed charge. So this is charge inside the surface. Charge inside the surface. But the important point is, on the left hand side you have got an electric field. This electric field is due to all the charges. This is due to all the charges. That means those charges which are also outside of the surface will also contribute an electric field. We are not going to write it for under the enclosed charge, but they will definitely have electric field. They will contribute to the net electric field for a very simple reason. Why we are not writing it for enclosed charge? For a simple reason that let's suppose that one of the electric field lines comes inside this surface, something like this, right? So number of electric field lines coming is 1 and it will also get out. So the net flux because of this charge, the net flux because of these charges will be 0, as the number of electric field lines which are entering the surface and which are exiting the surface are equal. So it will be the net flux will be 0 because of Q5 and Q6, whereas for Q1 electric flux is coming out, for minus Q2 electric flux is going out, and for Q2 and Q3 it is coming inside. right? So hopefully this is very clear that enclosed charge is only those charges which are inside the surface, and electric field is due to all the charges. Moving on, this law is very important. Moving on, we are going to call this surface as Gaussian surface. This imaginary surface is called is called as Gaussian surface. It is called as Gaussian surface. Now, some important points regarding this. First of all, statement: total flux emerging out of a closed surface is equal to the product of sum of enclosed charge by the surface and constant 1 upon epsilon naught. That means net flux will be written as enclosed charge upon epsilon naught. Q enclosed is the algebraic sum of all the enclosed positive and negative charges. Electric field due to charge outside the Gaussian surface contributes zero net flux through the surface, right? So hopefully this concept is clear to you. Now let's have a look. Let's suppose that you have got a sphere over here. Let's suppose that you have got a sphere, or let's suppose, let's start with some another example. Let's say that you have got a cube over here. Something like this. And on this cube, inside this cube, you have got one charge which is kept at the center and its magnitude is q. At the center, you have got a charge whose magnitude is q. You have to tell me the net flux linked with this cube, total cube. So you are going to say, sir, finally it's very easy. The net flux will be, in this case, it will be simply the total charge, that is q, divided by epsilon naught. This is the net flux. Okay, hopefully this is all good to you. Great. What will happen if I say that just tell me the flux, this charge was q, just tell me the flux linked with only this phase? Then what are you going to say? Only this phase. So if you are going to talk about only this phase, the total flux is q upon epsilon naught, and only because of this phase it would be q upon 6 epsilon naught, because there are 6 phases like this. Hopefully you are getting it what I am trying to say. Right now charge was at center. Let's say you have got same cube. Now the only difference is charge is actually not at center, but now charge is actually at the face of the cube. That means for this face it is at somewhere over here, that is q. So I'll also write it, charge is at the face of, and at the center, at the face of the cube, and you have to tell me the net flux linked with this cube. You have to tell me the net flux linked with the given cube, the total cube, right? So for questions like this, what we actually assume is, let's say that we are going to assume that there is also one more cube. That cube is drawn something like this. An imaginary cube drawn something like this. Hopefully you are getting it, what we are trying to do. Now because of this imaginary cube, now we will say that the net flux for both the cubes will be total charge upon epsilon naught, Gauss law. But in reality, there is only one cube. So we are going to say that that means the total flux will be half of this, as the another half of the flux will be linked with the another imagined cube, right? Hopefully this is all good to you. These are some pretty typical basic problems. Next is, let's suppose you have got a cube, or now what I'll do is I'll try to make you have got another cube, and now you have got charge at one of the edge somewhere over here. Now what will happen? Think about it. Pause the video or just give it a thought. What is going to be the net flux with this cube? Again, the idea is to draw the Gaussian surfaces, to draw more cubes, so that the charge is totally enclosed. Totally enclosed means it is totally contained by the surface. So now what we are going to do is we are going to draw some cubes. We are going to draw one cube beside this. Right? So this is, right now there are two cubes. Now we are going to draw another cube in front of this. And then we are going to draw another cube in front of this one. Hopefully you are understanding it. And then, so right now there are 4 cubes over here. And similarly there will be 4 cubes, 2 cubes over here and 2 cubes over here. Are you getting it? So in total, if you will see, we have got 1, 2, 3, 4, 5, 6, 7, 8. So there we'll require 8 such cube to completely cover this capital Q. Hopefully this is all good. That means the net flux in this case will be Q upon 8 epsilon naught. Hopefully this is clear to you. Now let's have a look at one of the questions related with this, and this was from JEE Mains 2025. They are saying that a square loop of sides A equals to 1 meter is held normally in front of a point charge. The flux of the electric field through the shaded region is this, where the value of P is, right? So value of P, we have to find out the value of P. First of all, let's find out the flux with the shaded region. My dear friends, if let's suppose we want to know the flux with the total region. Let's say we want to find out the flux with the total region. Total region means this total region, this one. Now we know that this looks like one face of the cube. So flux linked with one whole face is actually nothing but Q upon 6 epsilon naught, because as there are 6 faces. Inside this face, if you will see, we can actually break this region into, 1, 2, 3, 4, 5, 6, 7, 8 equal parts. We can break it into 8 equal parts. And out of those 8 equal parts, if I want to find out the flux through shaded region, I'll simply say that it is actually nothing but 5 parts of 5 out of 8 parts of the total flux, and the total flux is phi upon 6 epsilon naught. And this should be actually equals to charge, that is 1 coulomb upon epsilon naught, right. So this will be nothing but, this will be 5. We have to find out where the value of P is, right. So they are saying that the electric field, so it is actually 5 upon 48, and this is nothing but phi upon epsilon naught. Hopefully this is all clear. So the correct answer is going to be 48. So P is actually equals to 48. Hopefully you have no doubt. Moving on, now let's talk about some of the applications of Gauss law. For the application of Gauss law, the first one is long charged wire. If you remember in the last class, I think I hope I have derived the formula of electric field. I don't think we have done it, right? We have derived the formula of electric field due to a ring. We could have also done the same thing for a line charge also. We could use the integration, but right now what we'll do is, let's suppose that you have got a line charge, something like this, and you have got charges over it uniformly distributed, and we want to calculate electric field at a certain distance, let's say at a distance of r from it. So what we are going to do is, we are going to draw an Gaussian surface. Now there are certain rules of drawing Gaussian surface, and let me tell you what those rules are. Let's imagine a Gaussian surface as a cylinder for this particular case. And when you are going to imagine a cylinder, we'll actually assume it something like this. This is a Gaussian surface that we have imagined, a cylindrical Gaussian surface. So you can have multiple questions. First is, why only a cylindrical Gaussian surface? Why not a cuboid? Why not a cube? Why not a spherical Gaussian surface? Let's imagine, let's first understand what speciality this Gaussian surface has got. First thing is, the points that you must note for Gaussian surfaces, I'll write it under here, that Gaussian surface must be, it must completely enclose the charge body. Next is, you remember we can write this flux as the surface integral of E dot ds, isn't it? That means this thing will be written as E ds cos theta. So this angle theta, that means electric field must be either perpendicular to ds or electric field must be parallel to ds. This would be the best case. That means angle must be same. Now the problem with, let's suppose that you are imagining, let's suppose that you have got a line charge like this, and instead of talking about a cylinder, you are saying that let's consider it to be a sphere. So if you will consider it to be a sphere, okay fine, sphere will contain it. This is a sphere and it has contained it, no doubt about it. But let's suppose we are talking about a electric field will originate from positive charge like this, in this way. Fine. So sir, this is, let's suppose this is some ds. Let's suppose sir, this is some ds1. So ds1, area vector of ds1 will also be something like this, sir. Fine. At this particular point, angle is 0 degree, no doubt about it. Let's consider another ds like this. Ds vector will be in this direction, ds2, but now a electric field is in this direction. Are you getting it? And I don't know what this angle is. So similarly, you have got different ds all over the place. Different angle. Hopefully you are getting it. What's the problem when we'll consider it to when we'll consider the Gaussian surface to be a sphere? Whereas in this case, we can actually break down the Gaussian surface into three parts. First is the circular part. Second is the curved part. And third is again the circular path. And if you will notice, on this path, the area vector is something like this, the area vector is something like this, the area vector is something like this. So I am going to draw the area vector as ds2, ds1 and ds3. Hopefully it is clear to you. Electric field, whereas electric field will always be something like this. So for all points, electric field is actually, for this point, the angle between these two is, this is your electric field. Over here, angle between these two is 0 degree. Over here, angle between these two is 90 degree. Over here, the angle between these two is also 90 degree. What is 90 degree, dosto? The angle between the area vector and the electric field. So when we are going to write down the net flux, we are going to say it is basically the surface integral of surface 1, that is E ds cos 90, plus surface integral of surface 2, that is E ds cos 0, plus surface integral of E ds again cos 90. So this will become 0, this will become 0, and this will become E ds. That is the surface 2. Now surface 2, electric field is uniform everywhere. So we are going to write E times of ds for surface 2 equals to enclosed charge. Let's suppose the linear charge density is lambda. So we are going to write enclosed charge will be equals to lambda into L divided by epsilon naught. So this will become, integration of ds will become curved surface area, that is 2 pi RL equals to lambda into L upon epsilon naught. We can cancel out L, so we will get electric field as lambda upon 2 pi R epsilon naught. You can write it in vector forms, electric field will be in this direction. Hopefully this is all good. This is all clear. Moving on to the next application, which is an infinite plane sheet. So let's suppose you have got an infinite plane sheet. Now you have got a two-dimensional figure. Something like this, and let's say, by the way, this is a non-conducting sheet. So if we'll find out the electric field at any point, let's suppose we want to find out the electric field at somewhere over here. So what we'll do is we'll imagine a cylinder again, and we'll assume that it is trying to puncture it in this way. Please note that I don't need to now enclose the entire sheet. What I can do is first I'll enclose it something like this, and let's say it is somewhat puncturing it in this manner, coming out of the sheet something like this. Hopefully you are getting it. Now only you have got two surfaces again. Why? Because the area vector over here will be something like this. Area vector over here will be something like this. Area vector over here will be something like this. And electric field will be in this direction. Electric field will be in this direction. So there is no flux with this surface. So the net flux will be, let's suppose this area is S. This area is S. And the surface charge density of this sheet is sigma. That is total charge upon total area. So we are going to write the net flux will be, we have got two such surfaces. So 2 into E into S equals to enclosed charge will be sigma into S. Why sigma into S? Because this is the enclosed charge that we are talking about. Let's find out the electric field due to this much of the charge. Alright. So sigma into S divided by epsilon naught. So area can get cancelled out. So electric field will come out as sigma upon 2 epsilon naught, which is not dependent on distance at all. This is for non-conducting. This is not dependent on distance. Hopefully this is all clear to you. If it is conducting, it will be sigma upon epsilon naught. Moving on to a conducting sphere. If you have got a conducting sphere, the speciality with a conducting sphere is, now conducting sphere can be whether you have got a hollow conducting sphere or solid. If it is a conducting sphere, then they means basically same thing. Hollow sphere basically means hollow sphere, or you can call it as also a shell, conducting shell. It means that even if it is hollow sphere, basically means inside there is no matter. So the charge will only reside on the surface of the sphere. And even if it is a solid sphere, but conducting. Then also, even if you will supply some charge to the inside, it will automatically flow. It has got conducting properties, so it will automatically flow to the surface, to the maximum separation from each other, right? So even if it is a hollow or solid, both will have same derivation. Now let's suppose you want to find out the electric flux or electric field at a point which is less than the radius r. That means at an inside point. At an inside point. So inside point basically means let's draw a Gaussian surface from center to an inside point, and that will be drawn something like this. Right? So this is x. So we are going to simply say that net flux will be actually equals to E dot ds, integral of E dot ds, everywhere the angle will be 0 degree, equals to, there is no enclosed charge because all the charges residing on the surface. So electric field at all points which are inside this sphere is 0. Similarly, now let's assume that we are drawing a Gaussian surface outside the sphere, something like this, and let's say now this is your x in the second case, or let's say some r, and radius is capital R. Radius is capital R. So for B part, you have got x which is greater than capital R, that is the outside point. So for an outside point, we are going to say, see why I am saying that everywhere ds is angle between, let's suppose that my electric field will come something like this, and at this point the area ds will be drawn something like this. This is the ds. So at all points angle will be 0 degree. At all points angle will be 0 degree. So now what we are going to say is, we are going to say electric field E is uniform, integration of ds, that is 4 pi into r square, equals to enclosed charge is now constant, and total charge we actually will assume it to be capital Q, equals to Q upon epsilon. So electric field will become as 1 upon 4 pi epsilon naught Q upon r square. This is the formula. And if you want me to find it out on surface, so x will be equals to r, and then electric field on surface will be 1 upon 4 pi epsilon naught Q upon r square. Hopefully this is also clear to you, right? So this was for conducting hollow and solid, both. If it is conducting, if it is hollow or solid, there is no difference. Alright, so hopefully there is no trouble. Now the last derivation, that is the non-conducting sphere. So for non-conducting and non-conducting also solid, because even if let's suppose it is non-conducting and hollow, so this is plus, let's suppose I am talking about non-conducting but hollow. So this is also means the same thing. Although it is non-conducting, but it has nothing inside. So surface again will lie on the surface. So hollow conducting, solid conducting, and hollow non-conducting, answer will be same. But if it is solid and non-conducting, so this is non-conducting sphere and it is solid, then situation will change. Why it will change? Let's suppose this is the sphere that we are talking about, and now it has got charge all over its volume. like this, and volume charge density is rho. So please remember, volume charge density is rho, its radius is r. So rho will be actually equals to total charge q divided by 4 by 3 pi r cube. 4 by 3 pi r cube, right? And now let's suppose we want to find out at any inside point like this, and we want to know the enclosed charge. We want to find out the enclosed charge inside it, and this radius is let's suppose it is small r. So now what we'll say is that the enclosed charge will be actually equals to the density multiplied by the volume. So 4 by 3 into pi r cube. So it will be density is charge upon 4 by 3 pi into capital R cube. It is 4 by 3 pi into small r cube. So 4 by 3 pi can be cancelled out. So Q enclosed comes as capital Q small r cube divided by capital R cube. Now applying Gauss law, and for Gauss law we will say the net flux, that is the E dot ds, surface integral of E dot ds, is equals to enclosed charge upon epsilon naught. So electric field is E, surface area would be 4 pi into r square, small r square, enclosed charge will be, please remember that when we are talking about ds, it is the area of the Gaussian surface, right? And for a sphere, area would be 4 pi r square, and this is nothing but q into r cube divided by capital R cube. This will get cancelled out and electric field will come out as, and also here you have got 1 upon 4 pi epsilon naught q into r divided by r cube. So this is the formula that you will get for inside point. Let's suppose you want to find it out for an outside point. For an outside point, we will simply say electric field E into 4 pi into r square equals to enclosed charge is now capital Q, because I mean enclosed charge will be same, it is capital Q. So electric field will come out as E equals to 1 upon 4 pi epsilon naught into Q upon epsilon naught. Now please note that if somebody wants you to draw a graph of this thing, so you will draw the graph of electric field with the R something like this, that first it will increase at the center, it will be 0, it will get maximum at R equals to radius, and after that it will decrease, something like this. Hopefully this is clear. Now my dear friends, we are going to solve some of more questions regarding Gauss law in the next class, right? So hopefully you are comfortable with this. We will solve more questions but in next class. See you soon. Take care. Bye bye.